On November 10, 2022, a capsule the size of a small car fell toward Earth. Not from orbit, but from much higher. It had been launched specifically to die in the atmosphere. The mission was called LOFTID, which stood for something dry and technical. Low Earth Orbit Flight Test of an Inflatable Decelerator. But the question it was answering was anything but dry. Can we slow down something large enough to carry humans to Mars? The capsule hit atmosphere at 7.6 kilometers per second. Temperatures at its surface climbed past 1,600 degrees Celsius. And something remarkable happened. The inflatable shield held. 6 meters across, flexing under plasma, shedding heat into the void. For 4 minutes, physics and engineering fought each other violently. Engineering won, barely, and the capsule splashed down in the Pacific. NASA engineers in California cheered in a conference room. They had tested a concept, not a solution. And the difference between those two things is the entire story. The problem begins with the planet's indifference to human ambition. Mars has an atmosphere, but barely. 1% of Earth's sea level pressure, thin as the edge of a blade. Too thin to breathe, too thin to survive exposure. But thick enough to generate killing heat during entry at high velocity. This narrow window is what engineers call the worst of both worlds. Not enough drag to slow you down gently, enough to incinerate you. Every spacecraft that has landed on Mars faced this same knife's edge. Viking 1 in 1976, a 3.5-meter aeroshell decelerated and survived. Pathfinder in 1997, airbags cushioning the last drop to reddish soil. Curiosity in 2012, a 4.5-meter shield and an audacious sky crane. Each one worked beautifully. Each one carried robots. Curiosity weighed 900 kilograms, arriving at the Martian surface. A human mission to Mars with habitat, food, water, life support? That number climbs toward 20,000 kilograms, perhaps 40,000. Physics does not negotiate on the basis of human importance. More mass requires more deceleration, requires a larger heat shield. And that is where the wall appears, solid and invisible, unmovable. At NASA's Langley Research Center in Hampton, Virginia, a quiet crisis. Engineers have known about this problem since the Apollo era ended. The aeroshell that slowed Curiosity was 4.5 meters in diameter. It was the largest rigid heat shield ever successfully flown to Mars. Not because engineers lacked ambition, but because physics stopped them. To fit inside a rocket fairing, a rigid shield must be built to a limit. Current launch vehicles allow fairings roughly 5 to 8 meters across. Beyond that, you cannot get the shield off Earth in the first place. But the calculations for crewed Mars entry are unambiguous in their verdict. The required shield diameter sits between 20 and 30 meters minimum. No rocket on Earth, no rocket currently planned, carries a fairing that wide. This is the moment the problem sharpens into something almost philosophical. We can design the mission, we can plan the trajectory, we can train the crew. But we cannot build the door they need to walk through on arrival. The inflatable approach emerged from decades of aeronautical frustration. If a rigid shield cannot fit in a fairing, perhaps it does not need to be rigid. Pack it tight, launch it folded, inflate it in space before entry begins. The concept dates to research at Langley in the 1960s during Project Echo. Back then, material science was not ready. The idea was filed and forgotten. It resurfaced in the 1990s as the Inflatable Reentry Vehicle Experiment. A small prototype was tested. It partially worked. Funding dried up again. Progress in aerospace has always looked less like a straight line than a maze. The serious modern effort began with NASA's IRVE program in the 2000s. IRVE-3, tested in July 2012, reached Mach 10 with a 3-meter inflatable shield. The data was promising. The temperatures were survivable. The pressure held. But 3 meters and 7 kilometers per second is not Mars with 20,000 kilograms. LOFTID was the next step, the first test at operationally meaningful scale. 6 meters, Pacific Ocean reentry, conditions approximating what Mars entry needs. The results confirmed the concept survives at that scale. They said nothing about what happens when you triple the diameter. At JPL's Entry, Descent, and Landing Group in Pasadena, the numbers are sobering. Dr. Alan Chen led the EDL team that delivered Curiosity to Gale Crater. He described the 7 minutes of entry as terror compressed into procedure. Every event had to happen in sequence, on time, without deviation or recovery. Parachutes deployed at supersonic speeds, no parachute had survived before. The Sky Crane fired its rockets with millisecond precision above crater floor. It worked because robots can survive accelerations that would kill a crew. They can tolerate G-forces during aero capture that human bodies cannot absorb. They need no pressurized cabin, no seats, no structural margins for survivability. A crewed Mars mission changes every single one of those engineering equations. The heat shield must not merely survive, it must survive with humans behind it. It must not merely decelerate, it must keep deceleration within human tolerance. Astronauts can sustain roughly 10 Gs for a few seconds in trained condition. Mars entry for a large vehicle, done wrong, could spike at 20 Gs or beyond. The shield slows the vehicle, but how it slows the vehicle is equally critical. Shape, angle, center of mass. All of these feed into the survival calculation. The material at the center of everything is called heat T. Heat shield for extreme entry environment technology, developed at NASA Ames. It is a woven thermal protection system, tiles interlocked like carbon fabric. In laboratory tests, it has survived temperatures approaching 3,000 Kelvin. Developed through the 2000s and 10s in collaboration with contractors like Fiber Materials, HEEET works by ablation, controlled burning away of its own surface layer. The outer material vaporizes, carrying heat away from the vehicle in the process. It is self-sacrificing by design, each gram burned buying survival for what follows. Current ablative materials have been validated at diameters up to about 8 meters. The 4.5-meter Curiosity shield used pica, phenolic-impregnated carbon ablator. Pica was revolutionary in 2012, proven, reliable, understood at that scale. But pica at 20 meters has never been tested, never been manufactured, never existed. Materials do not always scale gracefully from test article to operational system. Seams between tiles become stress concentrations when the structure flexes. Flexure itself becomes a new problem when a 20-meter surface heats unevenly. One edge enters plasma slightly before the other. Temperatures diverge, forces twist. The structure must hold its shape while simultaneously trying to change it. This is not a problem that laboratory tests at 2 meters can fully predict. You cannot know if it works until you test it at the actual required scale. And testing it at actual scale means building it, launching it, and hoping. The inflatable approach solves the fairing problem, but introduces new ones. An inflatable structure packed into a small volume must unfold without failure. In space, with no technician present, with no second chance if anything jams. The bladder material must hold pressure against hard vacuum during transit. It must hold that pressure against aerodynamic forces during entry heating. Flexible materials that are light enough to fly behave differently than rigid ones. They vibrate, they flutter, they develop localized hotspots at flutter nodes. At hypersonic speeds, flutter can grow faster than any control system responds. The LOFTID test in 2022 flew for 4 minutes before Pacific Ocean recovery. Engineers analyzed the pressure data, temperature gradients, structural response. What they found was encouraging, but incomplete in the ways that always matter. The shield performed within predicted parameters throughout the test duration. It did not flutter catastrophically, did not lose pressure, did not rupture. But the test reached maximum conditions for only a brief window of seconds. Mars entry for a crewed vehicle would sustain peak heating for far longer. 4 minutes of acceptable behavior does not certify 20 minutes of survival. The gap between what was tested and what is needed remains uncomfortably wide. In 2019, SpaceX began testing Starship at their Boca Chica facility in Texas. The vehicle was designed from the beginning for eventual crewed Mars missions. Elon Musk stated publicly that Starship would solve the EDL problem for humans. The vehicle's stainless steel structure would act as its own thermal shield. Radiative cooling from the steel surface, supplemented by transpiration cooling. A system where liquid methane seeps through the windward surface and evaporates. Prototype testing proceeded through 2020 and 2021 with spectacular mixed results. SN8 through SN11 exploded during landing attempts, each failure revealing data. SN15 landed successfully in May 2021. The first complete flight test survived. Integrated testing with the Super Heavy booster began in April 2023. By early 2025, Starship had demonstrated controlled re-entry from orbital altitude. The heat shield tiles, 18,000 of them covering the vehicle's belly, performed. But Starship reaching Earth orbit is not the same as Starship entering Mars. Earth re-entry from low orbit involves about 7.8 kilometers per second. Mars atmospheric entry from interplanetary transit approaches 5 to 6 kilometers per second. The numbers seem close, but the atmosphere receiving you is completely different. Earth's atmosphere is 100 times denser, offering far more deceleration per kilometer. On Mars, you fall farther through thinner air before you slow to landing speed. Peak heating may be lower in absolute temperature, but duration extends longer. The total heat load absorbed, integrated over the full entry trajectory, may be similar. SpaceX has not publicly released detailed EDL analysis for crewed Mars missions. The heat shield tile system has not been tested in conditions simulating Mars entry. As of 2025, no organization has publicly certified any system for human Mars EDL. The weight constraint is perhaps the cruelest part of this engineering problem. A heat shield must be light enough to launch from Earth and reach Mars. It must be large enough to decelerate a crew vehicle from entry velocity. It must be strong enough to survive the thermal and mechanical loads of entry. These three requirements pull against each other without mercy or compromise. Making the shield larger means making it heavier, which means needing more fuel. More fuel means heavier launch mass, which means the shield must decelerate more. Which means the shield must be larger, starting the cycle again in a tighter spiral. Engineers call this the tyranny of the rocket equation, and it is genuinely tyrannical. Every kilogram saved on the heat shield is roughly 10 kilograms saved at launch. The ratio scales because of the fuel needed to carry fuel, the mass multiplier. At JPLEDL, engineers have modeled scenarios where the mass budget becomes impossible, where the heat shield required for deceleration weighs more than the vehicle can carry, where the only solution is a technology that does not currently exist in any form. The inflatable approach offers potential mass savings over rigid aeroshell designs. An inflated structure is largely volume, not mass, packing tightly for launch. LOFTID's 6-meter shield weighed 43 kilograms, an extraordinary ratio of size to mass. Scaled to 20 meters, assuming material properties hold, mass might reach 500 kilograms. A rigid 20-meter aeroshell of comparable performance might mass several metric tons. The difference matters enormously when every kilogram is fought over by competing systems. But those material properties, those scaling assumptions, remain unvalidated at full size. The history of spaceflight is a history of problems that seemed impossible until solved. The Saturn V's F1 engines suffered combustion instability that threatened the entire program. Engineers at Rocketdyne worked for years, testing hundreds of injector configurations. They solved it through empiricism more than theory, testing until the instability disappeared. They understood what worked before they fully understood why it worked. The Space Shuttle's main engines required redesigns that took a decade to complete. The solid rocket boosters used O-rings that failed in cold temperatures catastrophically. Every major space program has encountered its own version of the problem that should not exist. The Mars EDL problem is this generation's version of that apparently impossible wall. The difference is that previous programs had their impossible problems during the build phase. They discovered the combustion instability when they ran the engine, not before they built it. The Mars EDL problem is known, calculated, documented, and unsolved years before the mission. This is both the challenge and the opportunity that the situation presents. We know exactly what is needed. We know exactly what we have. We can measure the gap precisely. No surprises await us in the gap itself, only the hard work of closing it. The question is whether the closing happens before the mission is ready or after. Dr. Robert Braun spent decades at Georgia Tech and NASA studying planetary entry systems. In 2012, he published an analysis of the challenges facing human Mars exploration. His conclusion was careful but clear. Existing technology would not support a crewed landing. The mass fractions, the shield sizes, the deceleration profiles, nothing closed properly. New technology was required, specifically in the inflatable aeroshell and propulsion domains. Dr. Braun was not alone in this assessment. It was consensus among EDL specialists. A 2014 National Academies report on NASA's human Mars plans echoed the finding. The report identified EDL as one of the critical enabling technologies requiring development. Not refinement of existing approaches, but fundamentally new systems not yet demonstrated. A decade later, the gap has narrowed but not closed. LOFTID demonstrated inflatable aeroshells can survive at 6-meter scale. HEEET has been validated as a material capable of surviving extreme entry environments. Starship has demonstrated that large vehicles can re-enter and survive controlled flight. Each of these is genuine progress. Each advances the state of knowledge meaningfully. But none of them, individually or collectively, certifies a crewed system for Mars EDL. The path is clearer than it was in 2014. The destination remains the same distance away. In the physics of entry, everything happens in a compression of time. Entry interface to parachute deployment, roughly 4 minutes. Parachute deployment to ground, another 7 to 10 minutes of managed chaos. Total time from outer atmosphere to surface, less than 15 minutes. 15 minutes to convert interplanetary velocity into a survivable landing. Every system must work in sequence, and no sequence step has a recovery option. You cannot troubleshoot during entry. You cannot stop and assess. You cannot return. The vehicle commits to its trajectory at entry interface and follows physics from there. For robots, this is acceptable because robots carry no irreplaceable biological cargo. For humans, the stakes of a single failure in that 15-minute window are total. This is why certification matters differently for crewed missions than for robotic ones. A robotic mission that fails costs hundreds of millions of dollars and years of work. It is devastating scientifically and financially, but the loss does not include lives. A crewed mission that fails during EDL means the crew does not survive entry. The certification standard for human spaceflight reflects this absolute asymmetry. Every component must be tested to failure to understand its failure margin. Every failure mode must be identified and either eliminated or mitigated by redundancy. Testing at the actual operational scale in conditions approximating the actual environment. As of 2025, no heat shield system for crewed Mars EDL has passed this standard. Not because engineers are careless, but because the standard has not yet been met. The material has not been invented, tested, and certified. The phrase that frames everything. What would it take to solve this problem in time for a realistic crewed Mars mission? The most aggressive timelines from NASA and SpaceX point toward the 2030s as target dates. That leaves roughly 1 decade of development time from the current state of readiness. Inflatable aeroshell scaling must be demonstrated from 6 meters to something closer to 20. An intermediate test at 12 or 15 meters would provide critical data about scaling behavior. This requires a dedicated mission, likely launched from Earth orbit, not a small investment. The test vehicle must be large enough to be representative, heavy enough to stress the system. It must reach entry conditions similar to Mars, which means a specific trajectory and speed. Planning, designing, building, and launching such a test takes years from start to finish. After the test, the data must be analyzed, the design refined, the test repeated if necessary. Materials must be qualified not just for performance, but for long-duration spaceflight exposure. A transit to Mars takes 7 to 9 months, depending on the orbital geometry of the launch window. The heat shield spends those months in the radiation environment of interplanetary space. Cosmic rays, solar particle events, thermal cycling as the vehicle rotates in sunlight and shadow. Materials that survive 4 minutes of Pacific Ocean re-entry may degrade across 9 months of transit. This interaction between long-duration exposure and entry performance must be characterized. Every material property measured in a laboratory must be validated in the actual environment. The path forward exists. The steps are identifiable. The work is achievable in principle. Whether those steps can be completed in time remains the open question. There is a version of this story where the problem is solved elegantly and on schedule. Where LOFTID success in 2022 is the beginning of a rapid scaling campaign. Where each test fills in the data gap, each iteration improves the design. Where the certification of a crewed Mars EDL system happens by 2032 or 2033. Where the first humans on Mars walk out from behind a shield that did not exist in 2022. That version of the story is possible. It does not require any new physics. It requires funding sustained across administrations and economic cycles. It requires engineers solving problems that have never been solved before. It requires testing infrastructure capable of simulating conditions that do not exist on Earth. Most hypersonic facilities cannot reproduce the pressure, temperature, density of Mars entry. The density ratios are different. The gas composition is different. The heating mechanisms differ. Computational fluid dynamics can fill some of those gaps, but CFD is only as good as its models. Models for flexible aeroshell behavior at 20 meters in Martian conditions are not validated. There is no shortcut through this validation process, no substitution of simulation for test. The history of spaceflight is a graveyard of systems that performed perfectly in simulation, and then encountered the real physics of the real environment and failed in ways no model predicted. Humility before the unknown is not pessimism. It is the engineering culture that keeps crews alive. There is also a version of this story that is darker and more honest about timelines, where the scaling tests reveal nonlinear problems that do not appear until you try them. Where a 12-meter inflatable shield develops flutter modes that the 6-meter prototype did not. Where the tile bonding system that works beautifully at small scale fails at large scale. Where solving those problems requires years of iteration that the mission schedule does not contain. Where the crewed Mars mission scheduled for 2030-something slips to the 2040s. Not because of lack of will or resources, but because the physics takes the time it takes. The shuttle program was originally scheduled to fly operational missions by 1978. The first operational mission flew in November 1982, 4 years behind the original schedule. The James Webb Space Telescope was originally budgeted at $500 million and 10 years. It cost $10 billion and took 25 years from approval to launch. Space programs routinely take twice as long and cost 3 times as much as projected. This is not a failure of planning. It is the nature of developing unprecedented systems. You cannot schedule breakthroughs. You cannot budget for the problems you have not yet discovered. The heat shield for a crewed Mars mission is the kind of system history will surprise us with. Not with catastrophic failure, hopefully, but with problems that require more time than expected. The people who will solve this problem are likely already working in aerospace today. Some are at Langley, analyzing the LOFTID data, writing proposals for the next test. Some are at JPL, modeling entry trajectories for vehicle configurations that do not exist yet. Some are at SpaceX, iterating on tile designs that will someday survive a different planet's air. Some are graduate students whose dissertations are focused on hypersonic aerothermodynamics. None of them knows which specific insight will unlock the final piece of the puzzle. That is the nature of frontier engineering, working toward an answer without knowing its shape. The history of technology is full of solutions that seemed impossible until someone found them. The F-1 engine combustion instability was solved. Starship survived re-entry from orbit. Sometimes apparent violations of constraints reveal the constraints themselves were wrong. Other times they are solved through patient empirical work, trying things until one thing works. This problem has the character of the patient empirical variety, not the elegant reframing. It will likely be solved through a decade of testing, failure, revision, and retesting. Through engineers staying late to analyze data that does not behave the way the model predicted. Through funding committees saying yes when they might prefer to say not yet. Through intermediate successes that build the confidence needed to attempt the final test. When humans finally stand on Mars, the first steps will make headlines across the world. The names of the crew will be remembered alongside Armstrong and Aldrin and Gagarin. The images will circulate for generations, the reddish soil and pale sky and distant horizon. But the engineers who solved the heat shield problem will be less famous than they deserve. Their names will appear in technical reports, in acknowledgement sections of journal papers. They will attend conferences and present data to audiences who understand what they achieved. The heat shield itself will be invisible in those famous images, already discarded during entry. Burned and scattered across the upper atmosphere, its job complete, its existence unrecorded. This is how most engineering works. The solutions that enable everything else remain hidden. The successful mission is proof that the problem was solved, but it does not show the solving. The LOFTID test in November 2022 showed something important about what is possible. A 6-meter inflatable shield survived the conditions required of it in the environment that matters. 4 minutes of plasma, 1,600 degrees, and the structure held its shape and kept its pressure. It is a beginning, not a solution, but beginnings are where every solution eventually starts. The material that will carry the first humans through the Martian atmosphere may not yet exist. But the people who will invent it almost certainly do, and they are already working on the problem. The universe does not guarantee us Mars. It only leaves the possibility open for those who try. And the fact that we know exactly what we need, even when we do not yet have it. That clarity is itself a form of progress, a map of the work that remains to be done. Thank you for staying with us until the very end of this journey through deep time. If this exploration moved you, subscribe and stay for the next ancient chapter. Your curiosity is what keeps these lost worlds alive.